In this section, we're looking at the standard normal distribution. All of these are different graphs that describe the standard normal distribution, and you can see that some of them are shorter, some of them are wider, some are very flat, and some are very peaked. But each one has a particular characteristic that is going to be common with all standard normal distributions. This one over here on the right is the standard normal distribution that we'll usually be using. To get started, the standard normal distribution is based on a continuous random variable, like the uniform distribution was in our last lecture. That means it can achieve any particular value along an interval of numbers. So to get started, let's go ahead and look at some characteristics of a standard normal distribution. Now in the next unit the next homework we'll be looking at the normal distribution in general. Today we're just looking at standard normal distribution. So as I said, this is a continuous distribution. It can achieve any particular value over an interval. If you'll notice, each and every one of these distributions that we looked at above are symmetric. Now because they're symmetric, that tells me that the mean is equal to the median. Another way to describe this curve is a bell-shaped curve. It's also unimodal. That means it has one peak. That kind of goes along with that idea of bell-shaped. Also, f of x is greater than 0. So what this means is, and that's just greater than, not greater than or equal to, just greater than 0. What that means is all of this curve, this light blue line right here, is above the x-axis. It never falls below. So all the area is above, all the line is above the axis. It never touches or crosses the x-axis. The tails continue indefinitely in either direction. So again, it never crosses. Probably one of the most important things is the total area under the curve is 1. And this is just like the uniform distribution as well. And this is going to be a really important distribution characteristic that we'll use to solve all sorts of different problems. And just as a side note, another name for the normal distribution is the Gaussian distribution, or the Gauss curve. Gauss was a famous mathematician. Okay, so when we're talking about this distribution, this peak where this unimodal spot is, this is our mean, and it's also equal to our median. And remember, with the median, that was mu tilde. That's going to be the center of the distribution. And then the values to the right and the values to the left extend indefinitely, and this curve never crosses. A couple of things to think about. The total area under this curve is 1. So if I were to go through and shade all of this area, the total area that I could shade would be equal to 1. Now you have to be careful when you're sketching these curves on tests and on quizzes and even in your notes. Don't ever draw a curve that crosses the x-axis. So for instance, don't do this. A lot of people might go something like this. It never crosses this x-axis. So this is a bad way to draw it. When we draw these curves, we want it to go on indefinitely in either direction with that bell shape. So again, never crosses, never touches. Now when we talk about the random variable, x is, let's say, height, it could be weight, it could be length, it could be all sorts of different variables. For this particular example, we say x is distributed normally, n stands for normally, mu sigma. Remember, mu is the population mean, sigma is the standard deviation of the population as well. So this is in general. Now what we're looking at today for this section is the standard normal distribution. This is, again, the standard normal distribution. Now for the standard normal distribution, you can tell that mu equals 0. That's from right here. And the standard deviation is 1. In fact, I should come back here and erase this. This shouldn't be an x. This should be a z. Because when I'm talking about the standard normal distribution, I always use the random variable z. Now once we know all these different characteristics about the standard normal distribution, we can start answering questions about probability using the tables that I provided, and then also using your calculators for some shortcuts. Let's go ahead and start looking at a problem. Okay, to get started on our first example, we're going to be looking at the probability that our z standard normal random variable, so this is how we'd write this, the probability that z, our standard normal random variable, is, let's say, less than or equal to 1.37. Okay, now what this 1.37 represents, and we'll kind of make a few side notes here, this is the number of standard deviations we are above the mean. So this means, what is the probability of being less than or equal to 1.3 standard deviations above the mean? Now we know that this is the number of standard deviations above the mean because of the z. Now, as we talked about before, when we see z, automatically we would think distributed as normal, 0, 1. So to work this problem, the easiest thing to do is to go ahead and start with your normal curve. Now remember, a normal curve never crosses the x-axis, never goes below. Now the mean of this distribution, just as it says here, is 0. So here's my 0. Now I don't have to be too technical about this, but 1.37 is somewhere to the right of 0. Now remember, there's no area above a single point on a curve, so I can't find the area here. I need to have some sort of shaded area above or below. Now this says less than or equal to, so that tells me this is the area that I'm looking for. So this is the probability that z is less than or equal to 1.37. So that's the area that I'm looking for. Okay, so what we want to do, we can do two things. We can grab our z tables, our standard normal tables, and then we can also look at this in terms of a shortcut on our calculators. So let's go ahead and pop up our z tables. Now you have a copy of these z tables. To the left are our negative values. If you notice, we have a shaded region here. It's to the left. These values are all below 0. And to the right, these values are all above 0. Now the numbers inside the table are probability. The numbers outside the table are the number of standard deviations that value is above or below the mean. So let's go ahead and blow up our table and let's look at that value of 1.37. So here's 1.3. Let's go ahead and take a screenshot of this. And we want to make sure we have 1.37 involved in here, and then we'll pop this into our notes. Now when we're talking about the normal tables, we're talking about standard normal tables, we're actually looking for the values of 1.3, so this row right here, and in this column right here, 1.37. And you can see that they intersect right here at 0.9147. So that's the area to the left. So this area is equal to 0.9147. Now remember, the total area underneath the curve is 1, so any of our probabilities that we calculate have to be between 0 and 1. This particular area turns out to be 0.9147. Now in my math lab, be careful of how it asks you to round. Sometimes it'll say 3 places, sometimes it will say 4. So using our tables is pretty straightforward here. Now we can also use our calculators for a shortcut. I'm going to write out the command for your Texas Instruments calculator, and whether you have an 83 or an 84, this may change a little bit. But what we're looking for here is underneath the distribution tab, just like we used for the binomial distribution, we'd go second DISTR, and we would go down to the normal CDF. So we'd always want to choose the normal CDF here. Okay, so let's go ahead and start with normal CDF as our command. Remember, that's under the second DISTR. It's the second option, normal CDF. Now CDF stands for cumulative distribution function. So we're talking about the accumulated area to the left. So for the normal CDF function, what I do is I put in my lower bound, I put in my upper bound, and then I put in my mean and my standard deviation. So it always goes lower, upper, mean, standard deviation. Now for this example, that's going to be a little bit more difficult because we don't have a lower bound. So we'll choose normal CDF, and then for my lower bound, you can tell that this is going off toward negative infinity. I can't put negative infinity into the calculator though. So what we need to choose is just a very large negative number. So we could choose, let's say, like negative 100,000. Okay, and sometimes in your calculator it'll come up with negative 1 e to the 99th. If you want to use that, you can as well. Don't put too large of a number in here though, because sometimes you'll get an error. Now our upper bound, I want to go from negative infinity all the way up to 1.37, because that's my upper bound. My mean is 0 and my standard deviation is 1. So let's go ahead and put those values into the calculator and see what it returns. Now, like I said, this is my default for negative 1 times 10 to the 99th. I'm just going to go ahead and put in negative 100,000. So that's my lower. My upper is 1.37. Now those of you who don't have this menu, remember you'll just put it in straight from your calculator. Lower, upper, mean, standard deviation. Now if you notice here, it already gives me 0 and 1 for my mean and my standard deviation. So I'll hit paste, and you see the command goes in, and I'm hoping that I get a number similar to the one that we had when we looked up in the tables. Now if I highlight this command, and we'll paste it in here. So I get 0.9146, but for my answer I got 0.9147. But if you notice, if you go to the position, this would be tenths, hundredths, thousandths, 10 thousandths, 100 thousandths position. It would round this to a 7. So this would be 0.9147 as well. So our calculator gives us the same value, we just have to be careful about rounding. So this is what we're going to be doing over and over again, drawing that picture, writing out the statement, using the tables, and then checking also with our calculators. Let's go ahead and look at another example. For this example, we're looking at the probability that z, our standard normal random variable, is going to be less than or equal to negative 1.28. So the first thing we want to do is to go ahead and sketch a picture. That's always going to be helpful. Now because I have z, the standard normal random variable, I know the mean is 0. Negative 1.28 is somewhere to the left of 0, and this is that highlighted area that I'm looking for. So we're looking for this probability. So on my tables, what I can do is look up negative 1.28. Now that's going to be on the left-hand side under the negatives. So here's negative 1.2 would be this row right here. And then I'm going to go clear over to the 8. So negative 1.28 looks like 0.1003, this value right here. Okay, and that would be my solution, 0.1083. Now, we want to double check our work though. Remember, this is the area to the left. So when I put this in my calculator, this is starting at negative infinity and going to negative 1.28. So I'm going to choose second DISTR, choose normal CDF, and again I'm going to stick with that very large negative number, and here this will go up to negative 1.28. My mean is 0, my standard deviation is 1, and let's see what we get for our output here. I get 0.1003. That's different. Let me look at my normal tables. Negative 1.28. Oh, it is 0.1003. I just copied it down wrong. Okay, and then let's go ahead and take this screenshot as well. So 0.1003 is my solution. And again, you have to be careful about how you round these. So I need to update this because I copied down the value wrong from the table. 0.1003, 0.1003. Now this would of course round to 0.1003 as well, as long as I took it to 4 decimal places. Okay, let's go ahead and look at another example. Let's look at the probability that z is greater than or equal to 1.14. Okay, so this is a very different picture. It's still z, my standard normal random variable. Mean is 0. Here's 1.14 somewhere to the right. Now this is greater than, so I'm looking for this area right here. Now my tables do not give me get the area to the right, they give me the area to the left. So what I need to remember to use my tables is the total area underneath the curve is 1. So if I know the total area underneath the curve is 1, if I could find this value in the table and subtract it, I would be left with my shaded area of interest. So if I look up 1.14 in the table, and that's going to be over here to the right. So here's 1.101234. So 1.14 is 0.8729, this value right here, because it's 0.04 on the top. 1.1 across the side is 0.8729. So this value is 0.8729. And then to find my shaded area, I just go ahead and take 1 minus that value of 0.8729, and I get 0.1271. So this is my answer. So this is the area of interest, 0.1271. Now when we use our calculator for this, I'm going to use my upper and lower bound. So I'm going to go second DISTR, normal CDF. Now here my lower bound, remember it always goes lower than upper, you can see that my lower bound is right here at 1.14. Now my upper bound is what's different. My upper bound is going to be a very, very large positive number, so I'm going to put in a positive 100,000 here. My mean is still 0, my standard deviation is still 1, and then you can go ahead and hit enter, and you get that value right here of the 0.1271. Okay, now remember when you put these in your calculator, if you don't have that message box that popped up on mine, you have to remember the order: lower, upper first, and then mean and standard deviation next. And we can see that this goes ahead and rounds to 0.1271. Okay, so this is an example of using the fact that the total area underneath the table is equal to 1 to help us solve. Okay, let's look at another example. This is a between example. Let's look at the probability that z is between negative 1.23 and 2.45. Now when we look at this one, I'm going to use that idea of between. We know it's our standard normal random variable z, so negative 1.23 is somewhere to the right, 2.45 is somewhere to the, negative 1.23 is somewhere to the left, 2.45 is somewhere to the right, so this is my shaded area. Now if I use the table, what I'm going to do is I'm going to look up 2.45 and find all the area to the left, and then I'll look up 1.23 and look at all the area to the left and subtract them, and that will be left with my area of interest. So what I'm looking at here then is the values in the table. So this means this symbol is a Greek letter phi, it's a capital Phi, and it means to go ahead and use your normal tables and to look up 2.45. So this says to look in your normal tables and look up 2.45, and then I'll subtract, looking up in my normal tables, phi of negative 1.23. So let's go ahead and look up phi of 2.45. 2.4 down the side across, and I get 0.9929. Okay, so 0.9929. That would be the area to the left of 2.45. And then I subtract off the area to the left of negative 1.23. That's going to be over here. So here's negative 1.20123. Of course, my 0.03 is at the top. And I get 0.1093 here. So subtract a 0.1093. And then we go ahead and subtract the two. So again, I have that 0.9929 minus 0.1093, and I get 0.8836. So that is the total area right here. So this is the area that's shaded. Okay, now how would we do this on your calculator then? So we choose that second DISTR, normal CDF. Now remember, it's always lower bound first. Now if you don't have this little table on your calculators, you just have to put it in the order lower, comma, upper, comma, mu, comma, sigma. 2.45 is my upper, and my mean and standard deviation are 0 and 1. Okay, and then go ahead and hit enter, and then we'll go ahead and take a screenshot of this and compare it to what we have here. Now the problems that you'll see in this homework set will all have something to do with the mean of 0 and a standard deviation of 1. Okay, so this one looks like we're off by just a bit. So I have 0.8836 compared to 0.8835. So we'll have to be a little bit careful about rounding for these, but if we rounded both of these to the nearest 3 places, they would both round to 0.884. So sometimes the normal tables and the calculator won't be identical, but you can see they're pretty accurate out to 3 places for sure. So we've looked at upper right, lower left, we've looked at the between, and we can also look at problems where we're given the probability and then asked to look up our values backward. So for instance, we could be given something like, what is the probability that z is less than or equal to some value of c, and I don't know that value of c, but I do know the probability. And in this case, let's say that's given as 0.9345. Okay, so this picture looks a little different. This picture, I don't know exactly where I am, except on this distribution, because the area to the left is more than half, because half would be to the left, I know I'm somewhere up here. And I know that this total area is given to me as 0.9345. And what I'm asked to do is to find this value of c. Okay, so what I need to do is I need to look inside my standard normal tables and then find the value of c that makes this true. So this would look like phi of c equals 0.9345. So let's go ahead and grab our normal tables. We're going to be somewhere on the right hand side because I have that value that's more than 0.5, and I'm looking for 0.9345. Here it is. 0.9345 is 1.51. So that means I'm 1.51 standard deviations above the mean to create this value. So the value of c that will make this true is 1.51. Now how would you do this on your calculator? So on your calculator, we're not going to use the second DISTR and then normal CDF. What we're going to do is we're going to come down one more to inverse normal. Okay, so we're going to be looking at inverse normal. Now the area that I was given was the 0.9345, and then I have that mean of 0 and the standard deviation of 1 like I have for all of these. Go ahead and hit enter, and then we'll paste this in and see how it compares. So we can see when we plug in this function, it always goes shaded area first, mean and standard deviation. I get the same value for c here, rounded to the same values. Now you have to be careful when you're working with these. You have to be able to look at this and decide, you know, where the value of c goes. I can see that I'm above the mean here because I'm to the right. Because I have 0.9345 is quite a large number. Total area underneath the curve is 1. So that should help me find that value by knowing some of those characteristics of the curve. Let's go ahead and look at another example. Okay, here let's go ahead and look at the probability that z is between, remember the two less than signs is between 0 and c, is equal to 0.291. Now the key to these problems is to start with your curve sketch. Z is our standard normal distribution, so I start with a 0, and I know I'm between 0 and some value of c. Now what I know is this shaded region is 0.291. Now another thing that I know is this area to the left of 0 is equal to 0.5 because it's half my curve and my curve is symmetric. So kind of using our logic here, if I look at phi of c, if I add these two together, the area to the left is 0.5 plus 0.291 is 0.791. So let's go ahead and grab our normal tables again and let's look for 0.791. Now we can't always get exact. Oh, this one we do. 0.81. So I'm 0.81 standard deviations above the mean. And if you can't get exact values, you can go ahead and get to the closest value. So in this particular case, C is equal to 0.81. Now in your calculator, we'd have to go second, DISTR. I go down to inverse normal, inverse because I'm looking up the opposite. And I can't look up 0.291, I have to look up 0.791. And of course I have that mean and that standard deviation of 0 and 1. And it looks like I come up with 0.8098, etc. Okay, and let's go ahead and pop this in and compare our values. Now again, when we compare these, we can see that this would have to be rounded to agree, so 0.81. So our tables only go out to hundredths, but sometimes we'll be asked to look at problems that go out a little bit further. So for this next example, let's go ahead and look at something to do with percentiles. Now we've talked about percentiles before in Unit 1, and percentiles here are exactly the same as they were there, except now we have a continuous distribution. So let's suppose, S with a P hanging from it is suppose, we have temperatures that are normally distributed with a mean of 0 degrees and a standard deviation of 1 degree. What I would like to do is I would like to find the 83rd percentile. So with the 83rd percentile, what that means is I have all my data and I want to find the point such that 83% of the data lies below this point and 17% would lie above this point, because you can see that the total area here would be 100%. So this value right here is called P sub 83. So that's the 83rd percentile. So let's go ahead and look at what this would look like in terms of a curve sketch, and then we'll use our tables and our calculators to help us out here. Now, because I'm looking at the standard normal distribution, I have 0 and 1 here, so I could call this Z distributed normal 0, 1 instead of just temperatures like you'll see in some of your examples. 83% of the area is to the left, so what that means then is that I'm above 0, because I already know that this has to be 0.5 right here. So 83% of the area, 0.5 is right here, so 83% of the area would be at 0.33 here. So the total area is 0.83 then. So that's what I'm looking for, is this 0.83. So when we look at our table then, we're trying to find in our normal table 0.83 on the inside. That would be somewhere over here on the right. So I'm trying to get as close as I can to 0.83. So here's getting close, 0.8264, 8289, 8315. So if you notice, this is 0.0011 away from 0.83, and this is 0.0015 away. So this one's closer, so I'm going to use that value of 0.95 as my closest value. So going back and looking at our picture then, I can see that this is going to be 0.95. That is going to be my 83rd percentile. So 0.95 degrees, since we're talking about temperature here, would represent the 83rd percentile. Now on our calculators, the way that this would look is I would do second DISTR, inverse normal, because I know the shaded area. Now again, that shaded area is 0.83, and the calculator will be a little bit more accurate here because it can give me an exact value. The mean is 0 and the standard deviation is 1. Go ahead and hit enter. And you can see we get 0.954 here. We'll paste that in. So for my inverse normal command on my calculator, I get the same value, 0.95, if we were to round to the nearest hundredth. If I went out to thousands, it would be 0.954. So I can find percentiles also using these methods. Now, one of the most important things you can do is to create a good curve sketch, because that's really going to be helpful. Let's go ahead and look at another example. This example, let's find a percentile as well. Let's suppose temperatures are distributed normal 0, 1. That means I'm using our standard normal random variable. And I would like to find P, let's do 15. So this is the 15th percentile. Now what the 15th percentile means is that 15% of the data points lie below, and then of course that would mean 85% lie above. So 15% to the left would have to be this much smaller area here. So this is 0.15. My larger area is up here at 0.85. But I don't really care about that. I just want to find this value, and this will give me P sub 15. So let's go ahead and go to our normal tables. 0.15 is going to be on the left because I'm below the mean, and I'm trying to get as close as I can. So 0.1492 is 0.008 away. 0.1515 is 0.0015 away. So this one's closer. So this is negative 1.04. So this means I'm negative 1.04 standard deviations away from the mean. I'm 1.04 standard deviations below the mean. That's another way to look at that. So again, a good picture and coming up with this idea of if I'm above 0 or below 0 is going to be really important. Another key factor in solving a lot of these problems is to remember the total area underneath the curve is 1. So for this example, we're still going to look at temperatures being distributed normal with a mean of 0 and a standard deviation of 1. But this one has a bit of a story. These are temperatures, again, that we're looking at. And what ends up happening is we like to throw out the upper percentage and the lower percentage because they would be rejected because the temperatures are too high. So for this example, let's go ahead and find the cutoff point, and there will actually be 2 points here, above and below, to reject the lowest 5% and the highest 5% of temperatures. Okay, so again, a good curve sketch is going to be helpful here. So if we look at our curve sketch, we know our mean is still 0 because that's given here, 0, 1. Now, what about this upper and lower 5% business? Well, what that's telling me is the upper 5% of temperatures I want to throw out, and the lower 5% of temperatures I want to throw out. So I'm looking for the z value that gives me that. Now this lower one is going to be easy to find because the area to the left is 0.05. So let's go ahead and grab our normal tables here. And we're looking for 0.05 on the inside. Okay, we have this little asterisk here. 0.0505 and 0.0495. We can see that 0.05 is exactly in between these. That's why the asterisk is there. So it's exactly in between 0.04 and 0.05. So reading this down, this is a special case. It's not closer to 1 than the other. If it was closer to 1, I'd choose it. But since it's exactly in between, it's telling me I should use a z-score here of negative 1.645. And this is the exception. You'll see I have an asterisk here for that case, and I have an asterisk up here for the 0.005 case. And of course, I'll have those on the right as well. So they tell me here, 0.05, I should use negative 1.645. So this means I'm negative 1.645 degrees below 0, or from the mean. Now because of symmetry, because I know that this is a symmetric curve, I know that I'm 1.645 standard deviations above the mean on this side. So if I'm 1.645 degrees or higher, I would reject that temperature. If I'm 1.645 degrees below 0 or lower, I would reject on the other side. So it's really important that we be careful about how we look these up. And those two asterisks are kind of those different conditions. Now, I'm kind of reminded of another probability statement that we could probably look at again. What if we had the probability of z is greater than negative 1.23? And we're just jumping right back to some of the problems from the beginning. This takes into account that the total area underneath the curve is 1 again. So here, I know I'm 1.23 standard deviations below the mean, and I'm looking at the greater than case, so I'm looking here. So because I'm looking at the greater than case, if I look up negative 1.23, that's going to give me this area right here. So let's look up negative 1.23. Negative 1.20123.1093. And that doesn't still help me find this area though. So to find this area, what I need to remember is the total area underneath the curve is 1, and then I subtract out this red area that's to the left, and then that will leave me the area, this purple shaded area, to the right. So let's go ahead and take 1 minus that area, 0.1093, and I have for that upper right area 0.8907. Okay, so I'm still using that idea of the area underneath the curve is 1, and I can use that to help me find areas to the left and areas to the right, and the between areas as well, in order to try and figure out what's going on there. Now our calculator for this one, we would use not the inverse normal, but we're just going to go after that normal PDF. So second DISTR, we're going to choose normal CDF. Sorry if I said PDF, I meant CDF. Now you can see in our picture here the lower is negative 1.23. And my upper is just some really big number. And I like to use 100,000. If you use a number that's too big, sometimes you'll get an error message. Mean is 0 and a standard deviation is 1. Now remember, if your calculator doesn't have that shortcut menu, you just have to put in your numbers in the same order. So let's go ahead and paste this in and compare it. Okay, so my command here, normal CDF, is lower, which is negative 1.23, upper, which is this very large number. The mean is 0, and the next number here would be a standard deviation of 1, and these are separated by commas. So if I look at my values here, I can see that they are 0.8906. The 5 would round this up, and the 6 would go to a 7, so I get 0.8907 if I rounded this. I don't think we did a calculator command up here, so let's go ahead and look at a calculator command for this symmetric problem. So to do this problem, what I would do is I would use the inverse. So I do second DISTR, inverse normal. Now the x value, whoops, I hit normal, so let's try that again. Second DISTR, inverse normal. There we are. Okay, let me clear this out and try again. Second DISTR, inverse normal. Oh, okay, here we are. Now inverse normal, the shaded area is 0.05. That's the area to the left. And then I put in a comma. My mean is 0, and my standard deviation is 1. Okay, and I can see here that I get something pretty similar, and let's compare it to what we have when we use the tables. And I can see that I can round this to 3 places, and I'd get also that same value of 1.645. So that's using the inverse normal. Now remember, this is always going to be inverse normal. This would be the shaded area that's always to the left, mean and sigma. So those are kind of some of the things we need to look for. And now remember, because of due symmetry, if I'm 1.645 below the mean, I'm also 1.645 above the mean for the same area in the tails. And we're going to be using these ideas quite a bit over and over again, so understanding the idea of symmetry will be really important. As usual, if you have any questions, please let me know. Bring your questions to class. You can stop at the Math Center. You can also stop by during my office hours. Good luck.